This is tutorial number 17 associated with drill 14, and in this tutorial we're going to be discussing amplifier and oscillator principles. For the standard exam you do not have to know the circuitry operation of amplifiers and oscillators. However, you do have to know the principles behind amplification and oscillation. What are the things needed for oscillation? What are the things needed for amplification? And you need to know a little bit about the different types of amplification. That's what we're going to be discussing in this tutorial. Most of us are familiar with amplifiers. We come across them in everyday life. Our sound systems at home have an amplifier on them. The sound system operates at audio frequencies, so the amplifier on a sound system is an audio frequency amplifier. Audio amplifiers amplify audio frequencies, that is, frequencies that we can hear. Radio frequency amplifiers amplify radio frequencies which are well outside the human hearing range, but nevertheless the principles used to amplify audio and radio frequencies are pretty much the same thing. So already you are familiar with what amplifiers do. Amplifiers make the signal that we have bigger, larger, louder, stronger. That's what amplification is. Amplification don't do this for nothing. Amplifiers have to be connected to a power supply, and the energy that they need for amplification is provided to them by the power supply. In the amplifier there will be something like a vacuum tube or a standard transistor or a field effect transistor. There will be some sort of active amplifying device in the amplifier. What I want to talk about first is the different types of amplification. An amplifier is drawn on a radio circuit just as a block with the type of amplifier written in it. Now, unfortunately, well, perhaps even fortunately, there are a whole lot of different amplifiers used in radio, but they are all the same thing with some very, very minor changes in their characteristics. So you'll never see a block with just amplifier written in it. It might have IF amplifier, which is an intermediate frequency amplifier. It might have mic amplifier, which is an audio amplifier for the microphone. It might have AF amplifier, which is an audio amplifier for the speaker in a receiver. Or it might just have RF amplifier, meaning it's an amplifier designed to amplify radio frequencies only. Indeed, just about every stage of a radio transmitter or receiver is, in fact, some type of special amplifier, and we'll be discussing those in this and future tutorials. This tutorial is just on the principles of amplification and oscillation. Later on we'll talk about a little bit more about the specifics of some of them. If the amplifier on the screen was an amplifier that amplified everything without changing it, so if I were to put this signal into this amplifier and I were to get the same signal out except bigger, and the shape of the signal is exactly the same. I know I haven't drawn them exactly the same because I'm not that good a drawer, but if we put a small signal in and we get the identical signal out, and the only difference between the two signals is the output signal is larger than the input signal, then this amplifier is a linear amplifier. Very important that you understand what a linear amplifier is. A linear amplifier is one that amplifies without distorting the signal at all. It's just an amplifier. What goes in is what comes out, and it's just amplified. That is a linear amplifier. There is an amplifier called a non-linear amplifier, and we use many of those. And with a non-linear amplifier, if you put a full cycle of in, you might only get that much out. You might get half a cycle out. If you put, or you might put a whole cycle in, and you will just get a pulse, a fraction of a cycle. You just get a tiny sliver of the cycle out. So put one cycle in, you get a sliver out. Put one cycle in, you get half a cycle out. Any amplifier which does that is a non-linear amplifier. And naturally, if we're trying to amplify the signal coming from a microphone or coming into a radio receiver, we don't want to distort the signal at all. There are some special cases which I'll talk about which we do, but generally we just want to amplify, and we want to amplify without distortion, and to do that we have to use a linear amplifier. If we use a non-linear amplifier, it creates distortion, but there are reasons for doing that, and we'll get to them shortly. So we've learned that amplifiers, broadly speaking, are broken up into two categories. Linear amplifiers, ones that amplify without any distortion. Whatever you give them, they just simply make larger and give us more power. So a linear amplifier would be used to increase the signal strength of a single sideband signal. Nonlinear amplifiers distort whatever we give them to amplify, and we'll be learning shortly why that distortion can be useful to us. Amplifiers are broken into three broad categories. The first category, and you just need to know the categories and their basic characteristics. You do not have to know the circuitry diagrams for the standard assessment. The first category is Class A. Class A is normally used as an audio amplifier. It can be used as a speech amplifier, an audio amplifier. It can be used as an RF amplifier as well. It's not, however, because Class A amplifiers, well, it is used as RF amplifiers, but it's only used in cases where efficiency is not important, because Class A amplifiers are very low efficient. But what's the redeeming feature about a Class A amplifier is that it is extremely linear. Class A amplifiers are the most linear of all the amplifiers. So their claim to fame is linearity, and the problem with Class A amplifiers is they are very low efficiency. And efficiency is important because the power to an amplifier comes from a power supply. That power supply is probably only 50% efficient. The radio is probably only 50% efficient. So if we have low efficiency amplifiers, we're going to be generating a lot more heat in our transceivers, and that's going to reduce their lifetime. So Class A can be an audio or RF amplifier, most likely an audio amplifier, a microphone amp or a speaker amplifier. They are linear, but they have very low efficiency. The next class of amplifier is, I'm just adjusting my formatting here, if you'll forgive me for a moment. The next class of amplifier is Class B. Class B can be an audio amplifier, but the distinguishing feature of a Class B amplifier is that it is non-linear. It has non-linearity. It's a non-linear amplifier. whatever we give a Class B amplifier, it only gives us, if we give a cycle to a Class B amplifier, it gives us half a cycle out. So it's very non-linear. However, it is higher efficiency, much higher efficiency than a Class A amplifier. And we can do a trick. Even though a single Class B amplifier will only amplify half of the signal, one cycle of the signal, we can do a trick with Class B and use two of them. One to amplify half of the signal and the other to amplify the other half. And if we do that with Class B, we actually make a linear amplifier called a Class B push-pull amplifier. Not as linear as a Class A, but still linear enough to be used in radio transmitters and receivers without producing too much distortion. But basically, on its own, a Class B amplifier is generally a high-powered audio amplifier or a high-powered radio frequency amplifier. And we can use two of them to convert a Class B amplifier into a linear amplifier, in which case it's called Class B push-pull. The final class is Class C. Class C is extremely non-linear. The books don't say that, but I'm going to say it. It's extremely non-linear. It only, if we give a Class C amplifier one full cycle of sine wave to amplify, it may only amplify a few degrees of 1/2 cycle of it. You put a whole full beautiful sine wave into a Class C amplifier, and it might, for every sine wave, just give you a pulse out. And that doesn't sound like it could be very useful, but it is, because Class C amplifiers have very high efficiency. So if we're not worried about that distortion, that non-linearity, Class C would be the best choice. So there you have it. Class A, linear, low efficiency. Class B, non-linear, higher efficiency than Class A. I'll type that in. And the amplifier that has the highest efficiency of all is Class C. But all of the high efficiency amplifiers, Class B and Class C, are non-linear. Every amplifier has what is known as feedback. Some feedback. Now, you're familiar with feedback, but I don't think any person has ever heard a public address system where someone hasn't got the microphone too close to one of the speakers and you hear a howl, you hear a screeching sound in the speakers. Well, that's feedback. And you're familiar with that with audio amplifiers. You're familiar with it with audio amplifiers because you can actually hear the feedback. Amplifiers, all of them, have two types of feedback. The feedback is always from the output. This is the output of the amplifier. This is the input of the amplifier. And feedback is when energy gets back from the output of the amplifier to the input. And if that feedback reinforces the input signal, and I'll explain what that means in a moment, then the amplifier will howl. It will oscillate. In radio we say it oscillates. And you won't hear the howl unless it's an audio frequency amplifier. So if this is the signal going in, and this is the signal coming out, and it's just larger, it's been amplified, and if the signal that's being fed back from the output to the input, either deliberately or unintentionally, is in phase with the input signal, can you see that these two signals are in phase with one another? In phase means they follow each other. So the feedback signal is enhancing the input signal. When that happens, when we have positive feedback, in an amplifier, either deliberately or unintentionally, the amplifier becomes an oscillator. It will oscillate. It no longer amplifies, it howls. It either howls at a radio frequency. So an oscillator is just an amplifier with positive feedback. And we normally deliberately introduce that positive feedback. And you need to know this. Positive feedback is feedback that reinforces the input signal and causes the amplifier to oscillate. That's what we do when we don't want an amplifier. That's what we do when we want an oscillator. We get an amplifier and give it positive feedback. Because it's oscillating, it is now a source of a signal. It could be the source of a radio frequency signal. We could make a 10 megahertz amplifier oscillate at 10 megahertz and become an oscillator, in which case it would generate a radio frequency signal on 10 megahertz. In fact, an oscillator on its own with a power supply is the very simplest form of radio transmitter, and an oscillator is just an amplifier with positive feedback. So just revising that, an amplifier with positive feedback that we deliberately introduce, I'll just call it positive feedback to make it easy for me to write, that would produce amplifier oscillation, and the amplifier becomes an oscillator, becomes a source of a signal rather than excuse me, amplifying a signal. The other type of feedback is negative feedback. Now, all amplifiers have either negative or positive feedback. Sometimes we want amplifiers to be amplifiers and they have too much positive feedback and they begin to oscillate. So in order to negate the positive feedback and prevent the amplifier from oscillating, we can deliberately introduce into the amplifier negative feedback. Negative feedback. Sorry about the bad writing, but I'm sure you can read it or listen to what I'm saying. Negative feedback is feedback that's not in phase with the input signal. So if the input signal was like this and the output signal was amplified like that, then the feedback that we're giving back, if it's negative feedback, is out of phase like this. Can you see that this sine wave is out of phase with that sine wave? When this one is rising, this one is falling. So that's negative feedback, and that's how you combat positive feedback if you don't want it. In the power amplifier stage of all amateur transmitters, there is deliberate negative feedback because we do not want the power amplifier stage to oscillate, because that would mean the transmitter would transmit a signal even when the operator wasn't using the transmitter, because the power amplifier is oscillating. So in the power amplifier there's an adjustment for adjusting the amount of negative feedback to cancel out the unwanted feedback. And when we do that in an amplifier, when we use negative feedback to cancel out unwanted positive feedback, we call it neutralization. And it's a pretty appropriate word if you think about it. We are neutralizing unwanted positive feedback with deliberate negative feedback. And that is called neutralization, and we do that in amplifiers, particularly radio frequency amplifiers, to stop them from oscillating. So, what do we need for oscillation? What do we need to convert an amplifier to an oscillator? We're not building an amplifier, we're building an oscillator. Well, the first thing we need to do is build an amplifier, because to have oscillation we need amplification. we also need, with the amplification, we need to have positive feedback from output to input. So that's the second requirement for oscillation. We need amplification and we need positive, I'll just put positive there for positive feedback. There's one other thing we need besides amplification and positive feedback to get oscillation. Where will the amplifier oscillate? If we want the oscillator to amplify on 7 megahertz or 10 megahertz, we need some device in the amplifier to determine the frequency of oscillation. Normally, one of the things that's most often used is a tuned circuit, a parallel or series tuned circuit, because that will determine the frequency of oscillation. We need a frequency determining device. Amplification and positive feedback, they are the three requirements for oscillation, and you need to know that. When we have all of those things, we have an oscillator, and the symbol for an oscillator is just a circle with a sine wave in it. An oscillator is a source of radio frequency energy or audio frequency energy if it's an audio oscillator. An amplifier, on the other hand, is not the source of anything. An amplifier just amplifies our signal. We can use, instead of a parallel tuned or series tuned circuit, and by the way, you don't need to know this, but I'll give you the equation. The frequency of oscillation of this circuit is FR equals 1 over 2 pi, and you won't be tested on this, but I just think it's so handy to know. FR equals 1 over 2 pi root LC. So we can use this equation and tune this circuit to the frequency we want this amplifier to oscillate on, and in that case it becomes an oscillator. The problem with LC tuned circuits is that because they're mechanical, because the inductor's made of wire and the capacitor's made of plates, because they're mechanical, they're exposed to temperature change and expansion and contraction of the materials making up the inductor and the capacitor. Such an oscillator that uses an LC circuit may drift. Drift is a slow, unwanted change in frequency. They may drift. So you might turn the oscillator on at 7 megahertz and walk away, and 20 minutes later the oscillator's moved up in frequency or down in frequency by a few hertz, a few tens of hertz. That's called drift, and we don't want oscillators to drift, and that's the problem with these LC tuned circuits. Instead of using an LC tuned circuit, we can use a quartz crystal. The symbol for a quartz crystal looks like a capacitor, but it's not, because what it is a piece of quartz. That's quartz between two plates, and when a quartz crystal is able to vibrate, literally vibrate or resonate on any frequency we want, simply by changing the size of the quartz crystal. We don't file it down with a bastard file. The way you adjust the size of a crystal to a particular frequency is to hone the stone, the crystal quartz stone, down like a jeweler would hone it down using a very fine abrasive materials. Quartz is a piezoelectric material. What that means is if we put a voltage on a piece of quartz, it will twist. And if we remove that voltage, then the crystal will vibrate at radio frequencies for a little while. And it will vibrate or oscillate much longer than an LC circuit. Remember we talked about Q? If we made this circuit oscillate, this LC circuit oscillate, we would get a damped oscillation. And the reason why we get that damped oscillation is because of the losses in this circuit. It has low Q. Whereas if we use a quartz crystal, which has high Q, because once we put a bit of voltage on a quartz crystal and make it resonate, oscillate, it will remain oscillating and for much longer than an LC circuit. So it has a much higher Q and it's much more stable. It does not drift anywhere near as much as an LC circuit. That's why we use quartz crystals as the frequency determining device in most oscillators today. I want to talk a little more about linear and non-linear amplification. Linear amplification, if we put a single cycle of a sine wave into a linear amplifier, all it will do for us is amplify and give us a bigger signal on the output. That is a linear amplifier. And when we ever want to amplify a signal without changing it in any way, we must use a linear amplifier. But let's just have a look now at what a non-linear amplifier can do for us. Here we've got a non-linear amplifier. A non-linear amplifier distorts the signal that we put into it. We might put a full sine wave in and we may only get a pulse out, but it does something else. It creates a lot of distortion, and distortion is normally thought of as a bad thing, but in radio distortion is a good thing, or can be a good thing. If we were to put a signal into a linear amplifier, let's call the signal, and I drew sine waves before. If I were to put a signal F1 into an non-linear amplifier, at the output of that amplifier I would have that signal F1. It would be distorted, but I would have the same frequency. For every cycle that I put in, I may only get a pulse out, but those pulses are still at the same frequency as the sine wave. So if I put a signal F1 into a non-linear amplifier, I get the signal that I put in plus the signal that I get out. But being non-linear, I'm going to get harmonics of that signal as well. I'm going to get, at the output of the amplifier, I'm going to get 2F1. The second harmonic. I'm going to get 3F1. The third, that's the second harmonic. This is the third harmonic. That's the fundamental. This is the second harmonic, the third harmonic, and so on to the fourth harmonic. 4 times F1. So if this were to be 7 megahertz, the output of this would be 7, 14, 21 and 28 megahertz. Is that useful? Well, yes, it is. If we wanted to convert this signal from 7 megahertz to 14 megahertz, suppose we were to put a tuned circuit at the output of this amplifier, and that tuned circuit was resonant on 14 megahertz. Then what would happen? We'd put a 7 megahertz signal in. We would get 7 megahertz pulses coming out. If this was a Class C amplifier, those pulses would be coming out at the rate of 7 million a second, because our input frequency is 7 megahertz. Those pulses at 7 million per second would start this circuit resonating on 14 megahertz because it's tuned to 14 megahertz. So what we've actually done is enhanced the second harmonic. And when we do that, this is called a doubler. And doublers, because we want this distortion, are always Class C. If we were to leave the signal at 7 megahertz and put the output tuned circuit on 21 megahertz, then this would be a tripler. If we were to put the output resonant circuit on 28 megahertz, then this would be a quadrupler. Doublers, triplers and quadruplers are just Class C amplifiers with a tuned circuit in the output to enhance one of the harmonics, either the second, the third or the fourth. We don't normally go above 4. So we have doublers, triplers and quadruplers. And we do that to change a frequency from one frequency to another. In this case, we were changing 7 megahertz to 14 megahertz by using a doubler. There is one other thing, a non-linear, and I'll write it up just so you know I'm no confusion here. I'm talking about a non-linear amplifier. There's another thing a non-linear amplifier can do for us. Last time we just put one signal into the non-linear amplifier. We called that signal F1. And at the output of the non-linear amplifier we had the same signal F1. And we learned that if we put tuned circuits here, the frequency determining device, if we put tuned circuits there, we can accentuate either the second, third or fourth harmonic, and in which case we've turned the amplifier into a doubler, a tripler or a quadrupler, and we would use that to change the frequency of F1 to a different frequency. But what if we put more than one signal into a non-linear amplifier? What if we put two signals, F1 and F2? Well, we would certainly, whatever we put in, we get out. So if we put F1 in, we get F1 out. If we put F2 in, we get F2 out. However, we get some other interesting outputs as well. We get the sum and difference of F1. We get, assuming F2 is the higher frequency, we would get F1 plus F2, and that's a new frequency. Oops, F2, and we could call that F4 if you like, because we've created a new frequency here. And we get the difference. Presuming F2 is the highest frequency, we get F2 minus F1. And if we like, we can call that F5. And if we wanted to do this, we could put a tuned circuit in the output of the amplifier tuned to F4 or F5, and that would accentuate at the output these signals. So we've in effect changed F1 or F2 to a new frequency using this method. This is a very important method. All you need to remember that if you have a nonlinear, there are other products, by the way. These are called products. They're the mixing products, because when you have a nonlinear amplifier, you have mixing going on in the amplifier. And when you use an amplifier deliberately to mix, it's called a mixer, and we'll be talking about that shortly. This amplifier is indeed a mixer because it's nonlinear, and if we put two pure sine waves in, we'll get two pure sine waves out, or pulses out. We may not get pure sine waves. We can get pure sine waves by having a tuned circuit on F1 or F2, but we'll also get new frequencies, F4 and F5. And we can accentuate those frequencies by putting a tuned circuit here on either F4 or F5. And what we're doing is we're mixing. And that is probably one of the most useful things in radio, which I'll talk about next, because it's mixing which we use primarily to change from one frequency to another. To get our radio, we want our radio to operate on 28 megahertz. It might start, the oscillators might be on 7 megahertz, and somehow we have to mix that signal from 7 megahertz up to our transmit frequency on 28 megahertz. We would use a mixer to do that, and that's what I'm going to talk about very, very soon. What I've put up on screen is a mixer, and the mixer is just the amplifier we were talking about before. It's a Class C amplifier, and it could be used to amplify, but in this case we're going to deliberately use it to mix signals for us. And all Class C amplifiers, because of their non-linearity, mix signals for us. Now, into this mixer amplifier, and it's normally just called a mixer, but I'm trying to get you used to what a mixer is. A mixer is just a non-linear Class C amplifier. An oscillator is just another amplifier with positive feedback and a frequency determining device. And what we've got is an SSB signal that's got our voice on it, and we want to transmit it. And the rest of the radio prior to this has created this SSB signal for us. However, the frequency we want to transmit on is 28 megahertz, because I just made that up. We want to transmit on 28 megahertz. So somehow we've got to convert this 7 megahertz signal to 28 megahertz. And then if we do that, all we have to do is put it into a power amplifier and the antenna, and away we go. Can we use a mixer to do that? Let's have a look. Before we fed F1 and F2 into the mixer, F1 is now the 7 megahertz signal that we want to change the frequency of, and F2 is the oscillator. Suppose we put the oscillator on, and in the output here we're going to have F1, we don't want that, we've already got it. We're going to have F2, we don't want that, we've already got it. We're going to have the sum and difference, F1 plus F2, and assuming F1's the highest, F1 minus F2, and we're going to have some other ones too, but they're the important ones. So what if I put the oscillator on 21 megahertz? If I put that oscillator on 21 megahertz, then F1 plus F2, F1 plus F2 is going to be 28 megahertz. And that's how we change a signal from one frequency to another. That's one of the ways of changing a signal, one of the most common ways, the most common way of changing a signal from one frequency to another. When we use a mixer and an oscillator to do this, we give them a combined name of exactly what they do, frequency converter. A frequency converter. Now the problem with frequency converters is that they produce all of this rubbish at the output, and the only thing we want is F1 plus F2, 28 megahertz. So what we have to do, I'll just get rid of some of this text, we have to filter out of all the mixing products, we have to filter out the ones we don't want and just keep the one we do want, which is on 28 megahertz. I'm just going to give myself some screen space. So the product we want is F1 plus F2, and we have to get rid of all those other ones. So we need to put a filter here, and the filter we need to put is a bandpass filter. A bandpass filter just passes a narrow band of frequencies. It will only pass the frequencies that the bandpass is designed to pass. So suppose this bandpass, and I'll draw the symbol for a bandpass filter. That represents the symbol in the symbol, that represents high frequencies, mid frequencies, low frequencies, and we're passing a band of frequencies, so we put a stop on that one and we put a stop on that one. That's a bandpass filter. A low pass filter, I'm going off the track here, but it's just a good time to show you. A low pass filter, two sine waves, and we put a cross on the top one, so it's blocking high frequencies and passing low ones. That's a low pass filter. A high pass filter, we would put the cross on this one and it would show that it was passing high frequencies. and stopping low ones. But this is a bandpass. It's tuned to 28 megahertz, and it allows the F1 plus F2, which is a result of the mixing between F1 and F2. The sum F1 plus F2 is on 28 megahertz, and it will travel through that filter, and we've converted our 7 megahertz signal to 28 megahertz on single sideband. The bandpass filter not only passes the one we want on 28 megahertz, but it stops all the others that we didn't want. It stops F1, it stops F2, it stops F1 minus F2, and it stops all the others, and just gives us the signal we want. This is so important because this is done so often in radio. In fact, if you take away the mixers, amplifiers and oscillators, there's not much left in radio because in effect they're all the same thing. A mixer is just a non-linear amplifier. An oscillator is just an amplifier with positive feedback and a frequency determining device. So we will do this in a transceiver many times, and after the bandpass filter we're going to have a pretty weak signal here, so we would put another amplifier, an RF amplifier. But we'll be talking about block diagrams of transceivers well, we might be talking about it a little bit in this tutorial, but we'll certainly be talking in depth about single sideband and FM later on. In depth to the standard level anyway. So can you see what has happened here? It's very important. In fact, I'm going to do it again for you because it's just that important, because we're going to be talking about mixers and oscillators, frequency converters over and over and over and over again. So I really want you to understand this. If you put two signals, F1 and F2, into a nonlinear amplifier called a mixer, then at the output of that amplifier you will get the original signals F1 and F2, but you'll also get their mixing products, and the primary mixing products are F1 plus F2 and F1 minus F2. You will not be examined on this, but you do need to know how a frequency converter works. We want 28 megahertz. So what can we put our oscillator on to get 28 megahertz? If we put our oscillator on 21 megahertz, then F1 plus F2 is going to be 28 megahertz, and all we need then to do is put a bandpass filter in there to pass the mixing product we want, 28 megahertz, and stop all of this other crud. This is crud, that's crud, that's crud, this is the one we want. We put a bandpass filter on 28 megahertz, and what we've succeeded in doing is converting a 7 megahertz SSB signal to 28 megahertz. And that is the primary basis of radio transmission and reception. If you can understand that, I don't expect you to understand how the mixing occurs in there. It's quite complicated. It's very easy to demonstrate that it does occur, and mathematically very hard to prove it. It's easier to show you with a demonstration than to prove it, because you need some fairly difficult mathematics. That is a frequency converter. Please understand it. It's so important. It's probably the most, for me, it's the most important thing in the course for you to understand, because it will make understanding transmitters and receivers a whole lot better and easier for you. I just wanted, before leaving this diagram, I just wanted to talk about one other thing in brief. Oscillators are very delicate things. We are very concerned about their Q, and if we put a load on an oscillator, it's very much like putting the load on the engine of a car. The clutch system slowly engages the power of the engine of a car to the wheels of a car. If we were to engage the engine quickly, then the engine would stall. Well, oscillators can stall too, but they're not, you can't fry potatoes or cook chips with the power coming from an oscillator. They're very, very low power devices in the milliwatt range. And for that reason, it's very easy if we take too much energy from an oscillator, it will cause the oscillator to stop oscillating. So in order to overcome that, we put another stage but after every oscillator. It's not normally shown on circuits because it's presumed to be there, and it's just another amplifier, and it's called a buffer. A buffer amplifier is the full name. It's usually just called a buffer, and even though it's not shown on block diagrams, after every oscillator there will be, if it's a well-designed radio, a buffer stage. And the function of a buffer stage is just to lift the very low power of the oscillator up to a usable level before we send it to the mixer. And that protects, it insulates the oscillator from being loaded down by the mixer. And if the oscillator were to be loaded down by the mixer, it could stop oscillating. Of course, the radio wouldn't work. So just remember, after every oscillator stage, there is this buffer stage, which is a buffer between the oscillator and the rest of the circuit, so that the rest of the circuit doesn't stop the oscillator from oscillating. All amplifiers are capable of oscillation. So when radio amateurs build amplifiers, they try to avoid having unwanted tuned circuits in the amplifier. If there are unwanted tuned circuits, let's suppose the amplifier is designed to operate on 7 megahertz, and let's suppose that in the amplifier, unbeknown to the builder, there are resonant circuits on 7.1 megahertz. And let's also suppose there is enough positive feedback, and this amplifier, which is designed only to amplify 7 megahertz, begins to transmit a signal on 7.1 megahertz. That's not good. And that's called a parasitic oscillation. And I've brought a diagram of a transceiver that's very likely to have parasitic oscillations. Have a look at how this device has been built here, and it's a rat's nest of wiring all over the place. It's pretty messy. Well, all these little bits of wire have inductance. There's capacitance between all these little bits of wire. There are stray inductances and capacitances all over this circuit, and if this is an amplifier and it's designed to operate on 7 megahertz, and you might want to transmit on the 40 meter band, and your fellow radio amateurs say to you, hey look Joe, you're transmitting a signal on 7.1 megahertz as well as 7 megahertz. Well, that's probably due to the way this transceiver has been built with all this messy wiring and inductance. The way that would be fixed would be to clean up the wiring or just move it around. Maybe the stray parasitic circuit is in this part of the wiring loom here. So if we just pulled that around, adjusted it, we will change its resonant frequency, and that could stop the parasitic oscillation. A parasitic oscillation is an unwanted oscillation close to either above or below the operating frequency. That's not a harmonic. A harmonic is a multiple of the operating frequency. If a transmitter was transmitting on 7 megahertz, the second harmonic would be 14, the third harmonic 21, the fourth harmonic 28. But let's suppose you're putting out a signal on 7.2 megahertz. That would not be a harmonic, that would be a parasitic oscillation. Even though we're not doing transmitters in this tutorial, I thought that this would be an opportune time to bring some of these oscillators and amplifiers together and show you the block diagram of a Morse code transmitter. It will just help fit it together and hopefully help you remember it all. A Morse code transmitter just transmits a carrier wave, a sine wave, at radio frequencies on and off. So what we've got here is a 7 megahertz oscillator. That would be the carrier oscillator. We don't want to transmit on 7 megahertz. We're just starting out on 7 megahertz. We don't have oscillators running on very, very high frequencies because they tend to drift. So we always have our oscillators generally on pretty low frequencies so that we control the drift a little bit. So the carrier oscillator is just an amplifier with positive feedback, and it would have a crystal in it for stability. The buffer stage is so that the carrier won't be loaded down by the following stages. If we didn't have the buffer stage, every time we sent Morse code on the Morse key, the carrier oscillator could shift slightly in frequency, and that would sound like a chirp, and that's why it's called chirping. It's the pulling of the carrier oscillator. Well, the buffer prevents that from happening. There would be a buffer here as well. I haven't drawn it. Normally buffers aren't drawn, but after every oscillator there would be a buffer. So at this point here after the buffer, we've got a 7 megahertz signal, nice clean sine wave. The key turns that on and off. The RF amplifier simply amplifies our 7 megahertz. So at this point here, we've got a 7 megahertz signal that is being keyed on and off by the Morse code key. And we want to transmit on 28 megahertz, but at this point we're on 7 megahertz. So we are going to use a mixer and an oscillator to change frequency from 7 megahertz to 28 megahertz. Remember, out of the mixer comes a whole lot of mixing products. There'll be 7 megahertz here, there'll be 21 megahertz there. There'll also be the sum and the difference, and it's the sum of 7 megahertz plus 21 megahertz which gives us our output frequency of 28 megahertz. Because we get all this crud at the output of the mixer, we need a filter to stop all the crud and just allow what we want to pass through. So we have a bandpass filter. That bandpass filter would be on 28 megahertz, and it would pass a narrow band of frequencies for a Morse code transmitter. Morse code transmission's about 200 hertz wide, so this filter need only be 200 hertz wide bandpass. And if that were the case, we would have to use a crystal filter in there. So the frequency converter, comprising of the mixer and local oscillator, transforms the 7 megahertz signal here to a 28 megahertz signal there. The bandpass filter gets rid of everything else, just passes the 28 megahertz Morse code signal to here. The power amplifier brings it up to say 100 watts, and away we go with our Morse code transmitter. You know, every stage in this block diagram is really an amplifier except the filter. The oscillator is an amplifier with positive feedback and a crystal. The buffer is just a linear amplifier. The RF amplifier here could be non-linear because we can use a non-linear amplifier with Morse code. Probably would be for efficiency. This mixer is just another special amplifier. It's non-linear. It has 2 inputs, 1 output, and because it's a non-linear amplifier, it mixes all the signals that go into it. And we're using that mixing to generate for us a shift from 7 megahertz to 28 megahertz of the CW signal. The bandpass filter removes everything except the signal we want, the one on 28 megahertz. The power amplifier amplifies that signal up to transmit level, and we go up the antenna, and there's the basics of a Morse code transmitter. And if you understand that, if you understand the block analysis of that, you're not going to have a lot of trouble understanding transmitters and receivers, because it's the same principles over and over again, particularly this one here of mixing to change frequency. That combined function of an oscillator and a mixer is called a frequency converter. Well, that's it for now on amplifiers and oscillators. We're going to be talking about transmitters in the next tutorial and in quite a few thereafter. So don't be too concerned about transmission and reception yet. Just be concerned about whether you understand the principles of oscillation and amplifiers, the way they can be linear or non-linear, their use as a mixer. If you want an amplifier to oscillate, you need positive feedback. If you don't want an amplifier to oscillate, you need negative feedback, and that process is called neutralization. Applying an equal amount of negative feedback to cancel out positive feedback is called neutralization, and radio amateurs do that with their power amplifiers in their transmitters all the time. Rightio, right now we're going to start going through some of the sample questions on this subject, and that'll also be an opportunity for me to see if I've left out anything as well. Okay, section 14, oscillators and amplifier principles, and let's go through some of the exam questions or types of exam questions that you're likely to get on this subject. Question 14.1. Positive feedback from output to input is essential for normal operation in, or we need positive feedback for oscillators. We also need amplification, so we need an amplifier, and we also need a frequency determining device such as an LC tuned circuit, or better still would be a crystal, quartz crystal, piezoelectric crystal. 14.2. The carrier frequency of a simple CW, that's Morse code transmitter, is generated by, and if you remember the block diagram I put up of a CW transmitter, the carrier is generated by an oscillator stage. The only stage that generates a signal from nothing is an oscillator. The simplest form of transmitter is a power supply and an oscillator. Even better would be a power supply, an oscillator, and an amplifier. Move on. 14.3. Crystal oscillators are often used for frequency control in transmitters because they are more stable than LC oscillators. The main feature of a crystal oscillator is its stability. They do not drift as much. They do drift, but nowhere near as much. You need to remember what drift is. Drift is a slow, unwanted change in frequency. Question 14.4. Scroll a little bit. A frequency multiplier stage, that means a doubler, a tripler, or a quadrupler, doubles, triples, or quadruples the input frequency. So a frequency multiplier stage is unlikely to oscillate because the input and output frequencies are different. For oscillation to take place, the input and output frequency has to be the same, and there has to be positive feedback. So doublers, triplers and quadruplers, they don't need neutralization because they're very unlikely to oscillate because the output tuned circuit is tuned to a different frequency to the input. 14.5. To keep a circuit oscillating, is it essential to maintain positive feedback between output and input? Oscillators need positive feedback. Question 14.6. A feature of a Class A amplification is? Well, a Class A amplifier is not very efficient, but it is extremely linear. That's the really good point about a Class A. Extremely linear. Question 14.7, similar to a previous question, the function of a doubler stage in a transmitter is to multiply the frequency of the incoming signal by 2. And we covered that in the tutorial. And if you're confused about it, go back and have a look at the tutorial again. 14.8, if a radio frequency amplifier is to be operated as a frequency doubler, the output tuned circuit will be tuned to twice the input frequency. If it was a tripler, it would be 3 times. The output would be tuned to 3 times the input frequency. Quadrupler, the output would be tuned to 4 times the input frequency. And a doubler, tripler, or quadrupler would be operated in class C. Question 14.9. The function of a tripler stage in a transmitter is to multiply the frequency of the incoming signal by 3. I think you pretty well got that by now. 14.10. A single sideband suppressed carrier signal on 9 MHz may be changed to a single sideband signal on 21 MHz by frequency mixing. We would have to put the 9 MHz signal into a mixer along with a signal from an oscillator. What's 9 from 21? That's 12. So if we had an oscillator going to a mixer on 12 MHz and our wanted signal on 9 MHz, then one of the outputs from that mixer, oh, hang on, I've just made a blur. We want to change it to 21 MHz. Yeah, that's right. So we would have our oscillator on 12, feed that into the mixer, our wanted signal on 9. 9 plus 12 is 21 MHz. We use a frequency converter, a mixer and an oscillator on 12 MHz to move a 9 MHz SSB signal to 21 MHz. 14.11. An audio amplifier is operating in class A. Is highly efficient? Well, class A is not highly efficient. Likely to cause severe distortion? No, class A is linear. It's a linear amplifier. That's the answer. 14.12. A feature of class C amplification is, well, class C is very nonlinear. So it's not linear. Non-linear operation, that's the answer. Oh, high efficiency. Actually, there are 2 correct answers here. So I'm just going to mark it as 2 correct answers, and I'm sure that the drill is only going to have 1 correct answer. I'll check that in the drill. But a class C, the features are non-linear operation and high efficiency. So there's 2 correct answers there. Sorry about that, but it doesn't hurt. I'll just make sure that in your drill there's only 1 correct answer, but it doesn't hurt in the tutorial to have 2 correct answers. That's just an error on my part. So class C, its features are non-linear operation and high efficiency. Just remember, in your exam there will not be 2 correct answers ever. 14.13. The highest power efficiency in a radio frequency power amplifier is obtained when it's operating, well, we haven't spoken about class AB, that's between A and B. We're only concerned about classes A, B and C, and the most efficient class of those is class C. The least efficient is class A. Is class A, and it is linear, and class B is higher efficiency than class A, and it's also can be a linear amplifier if we use 2 of them, but one class B on its own is non-linear. And class C is certainly the most efficient. The efficiency of class C, you don't have to remember this, it's between 60 and 80%, which is quite efficient, and it's very non-linear, extremely non-linear. That might help. Question 14.4. An amplifier stage operating in class C is biased. Oh, I'm not really sure if you need to know this, but because I didn't cover it. I'm sure I'll cover it later. I'll have to check the syllabus. But a class C amplifier is biased beyond cutoff. I'll have a look and see if we need to do more on that one. but Class C is biased beyond cutoff. I think that might be an advanced sample question that's stuck in there. Question 14.5, a feature of Class B amplification. A, higher efficiency than Class C? No, it's not. Class C is the most efficient. Higher efficiency than Class A is true. Class A is about 20 to 25. Class B can be about 35 to 40% efficient. You don't need to remember those exact figures. A Class C amplifier has an expected theoretical efficiency of about 65%. It can be higher than that, it can be 60 to 80%, but it'll always be clear if you're asked the question. It's the highest efficiency between 60 and 80%. 14.17, a feature of Class C amplification. Yeah, I hope I don't have two correct answers in this one. Well, it's not linear, it's not low resistance, it is high efficiency. Class C amplifiers are very efficient. 14.8, the purpose of neutralizing an amplifier is to prevent generation of unwanted oscillations. If we have positive feedback in an amplifier, we have to deliberately apply negative feedback to cancel out that positive feedback to prevent that amplifier from becoming an oscillator. Question 14.19, a process which should be used to prevent the power amplifier stage of a transmitter from generating some unwanted oscillations is called neutralization. 14.20, parasitic oscillations are suppressed by removing the unwanted resonances in the circuit. Do you remember that diagram I showed you of that bird's nest construction of a transmitter? That circuit would have been full of unwanted resonances, and the way to prevent parasitic oscillations from occurring, we would have to remove those resonances. Those stray resonance circuits. 14.21, in a single sideband transmitter, parasitic oscillations would most likely occur in the power amplifier stage. Question 14.22, the factors which are most likely to cause parasitic oscillations in an RF power amplifier are stray circuit inductance and capacitance. Question 14.23, in an RF power amplifier, parasitic oscillations are most likely caused by, again, stray circuit inductance and capacitance. Well, that's it for amplifier and oscillator principles. I may well add a couple more questions to your drill just to help you a little bit that aren't here. So I'll see you again in the next tutorial. We're going to be talking about transmitters, I believe. So I look forward to seeing you there, and I hope your course is going well. Cheers for now. This is Ron, VK2DQ.